Hello, everyone. Today, welcome to the Spark and AI Summit 2020. Today, I'm going to talk about cloud-native Spark scheduling with the YuniKorn scheduler. I'm Li Gao. I'm the tech lead and engineer at Databricks Compute Fabric, and previously I was the tech lead at data infrastructure at Lyft. Today, I also speak with Wei Yang. He is the tech lead at Cloudera Compute Platform, and he is also the Apache Hadoop committer and the PMC member, and he is the ex-Alibaba and IBM. Today's agenda, I will start talking about why Lyft is choosing Spark on Kubernetes to run our Spark workloads, and then talk about the lead for using a custom Kubernetes scheduler for optimizing Spark running on Kubernetes. Then Wei will start talking about this Spark scheduling with the new Apache YuniKorn scheduler, and we will provide a deep dive into the YuniKorn features. And lastly, we'll share the community and the roadmap of the YuniKorn scheduler. The Kubernetes is being used widely at Lyft for both data and services. And in this picture, showing the landscape on the data side, at very high level, our data use cases at Lyft, including business intelligence BI use cases, mostly based on Apache Superset for user interaction. And then we have the machine learning and the deep learning data scientists using the Jupyter notebook to interact with our data. And on the data engineering side, most of our data engineers are leveraging the open source Apache Airflow to authorizing ETL workflows. All those different use cases are leveraging these different data compute processing engines, Apache Spark mainly for our batch compute and many of our jobs, and interact with machine learning and deep learning engines. And we also have the Presto for our interactive query engines, and we have Julie for our real-time metric store and compute. And all these compute engines are running on our compute infrastructure, which is mostly on Kubernetes and some still on EC2. And all the data in our data landscape live in the cloud storage, which is S3, our data lake, and then some of the metadata on the RDS. Why we choose Kubernetes for Spark? Kubernetes is currently the most active orchestrator, open source orchestrator for containers. And the benefit of choosing a containerized Spark compute is it provides us a shared resource across different machine learning and ETL jobs. And it also supports multiple Spark versions, like Python versions that our customers need. And with the containerized approach, we also can enable version control containers on the shared Kubernetes cluster for both faster dev iterations and for our stable productions for rollback and roll forward. There is also, with the Kubernetes engine, it provides us opportunity for a unified and advanced observability and resource isolation support across our data compute and our microservices. And with the Kubernetes support also comes with the support for finer grained access control that is very beneficial for us to support many compliance and security use cases on this shared compute resource. Now let's talk about, dive a little bit deeper into how Spark on Kubernetes is used at Lyft. This is a very high level overview how Spark is being used at Lyft. For all our jobs coming through, we call a data infrastructure gateway, which route the traffic across many of our compute resources based on labels. And the label will shuttle to different cluster pools. Within a given cluster pool, there could be one or more Kubernetes clusters. They can share one or more S3 bucket as our persistence storage, and some of them may have their own dedicated storage for privacy and security reasons. And all those jobs on the compute side also share the same set of metadata, which is their schema metadata, lineage, and discovery metadata. Now let's dive a little bit deeper on how a Spark job is launched on Kubernetes on the Lyft environment. When a job comes in through this data infrastructure gateway, the first with the labels, or we land on cluster pool. And within cluster pool, we have a concept called cluster pool controller, which will route to a specific Kubernetes cluster. And within the Kubernetes cluster, specific Kubernetes cluster, we have a concept of namespace group and the namespace group controller, which can split the job into different namespaces. And once it lands on a specific Kubernetes namespace, it can materialize a Spark CRD, which is an object supported by the open source Spark on Kubernetes operator that is open source by GCP, the Google Cloud Platform. And once the CRD is being read by the controller, it will materialize the Spark executor and driver pod on Kubernetes, and finally the compute can start and talk to the data lake. Even with that design, we noticed after our production of the system, there's problems with those Spark on Kubernetes infrastructure. The first noticeable issue we have with this design is the complexity of the multiple layers of controllers to handle the scale of the system. And then because of the multiple layers of controllers, their latencies in certain cases can be amplified from the lower layer to the upper layer. And on top of those two issues, we also noticed as we added more features, there are requirements for different priorities to share between jobs, clusters, and namespaces, which is very difficult to manage and coordinate among the different layers. Now let's focus into the single cluster. Even with a single cluster, we noticed with the default scheduler, there are issue with high latency. This can happen when we have a very large volume of bursty batch jobs, and we observe in certain cases can go hundreds of seconds of delay before a given Spark pod can be executed on a given node. The next issue we notice is on the other end, when we have a very large batch job sharing the same resource pool, it becomes unpredictable for fair sharing among those pods, and it's undesirable for our end result. We talked about the different queue requirements. We have a need for both FIFO and fair sharing resource, a need for a job cluster, and which is not well supported by the default scheduler. And then there's as more jobs coming in, especially on the data engineer side and data science workload side, there is a need for elastic and hierarchical support for this priority management, which is lacking on the default scheduler to schedule pods. Lastly, there's a desire from our customers that want to pour some of our visibility into scheduling behavior that we used to have on the Hadoop Yarn world into the Kubernetes world, and that is lacking with the default scheduler. And lastly is we want to, with this custom Kubernetes scheduler, we can have a simplified layer of controllers on our implementation. Now I'm handing over to Wei to talk about the Spark scheduling with YuniKorn, with the introduction of the YuniKorn scheduler.
Okay, this is Wei, and moving on, I will be introducing the Spark scheduling with YuniKorn and some of deep dive into the YuniKorn features. So first of all, there are several flavors to run Spark on Kubernetes. One is the native Spark on Kubernetes, which is actually user can run the Spark submit that launches Spark driver pod. Then the driver pod will applies for request for the executor pods. And the other approach is to leverage the Spark Kubernetes operator, which is open source by Google. And instead of submitting jobs by Spark submit, it creates a Spark application CRD then the Spark operator will help to manage the life cycle of the job, Spark job, for you. And for the resource scheduling in Kubernetes, when we run Spark, we first need to understand how the resource scheduling is working in Kubernetes. So the default scheduler workflow is quite simple. In human language, it is like the scheduler picks up a pod each time and find the best fit node, then launch the pod on that node. Since Kubernetes 1.15, it provides the scheduler framework where you can actually plug a certain number of extensions to the framework. You can do some filtering, you can do some ordering, but overall the workflow is the same. Then let's say what kind of scheduling challenges we have when we run Spark on Kubernetes. Our purpose is to move the Spark workloads from the legacy Hadoop clusters to Kubernetes-based clusters, because this will give us a unified architecture for compute platform that supports multiple environments on-prem, on cloud, hybrid cloud. And Spark is a super powerful compute engine, right? It has multiple workloads, it supports multiple workload types, which includes the ad hoc queries, the batch jobs, and the workflows, and streaming jobs. So this when they combine together is quite complex runtime for the platform. And when we do the job to move Spark to Kubernetes, we noticed some of the challenges, which mainly in two categories. One is the job scheduling. Because we have so many jobs running in a shared environment, possibly from multiple tenants, multiple users, teams, groups. So the job ordering becomes very important. And also the job queuing, there's no queuing for the jobs. And secondly, the job level priority is also important to ensure some of the urgent jobs can run. And resource fairness becomes important when we want to share the resources between jobs or the namespaces, the queues. And also the gun scheduling. The need for gun scheduling is very essential for the machine learning workloads, as well as for Spark. So the second category is the resource sharing and utilization. What we have observed is when we run Spark on Kubernetes, the utilization is not that good. And sometimes the Spark driver pods occupy all the resources in the namespace. And sometimes there's a resource competition, which happens when it happens, the big jobs get starved. And also there are some other misbehaved jobs. By that I mean when some of the job have some bad configuration or is being picky on nodes, and depending those jobs will waste the cluster resource. And also another important factor is the throughput. So for a batch-oriented system, the throughput is very important to ensure the latency. And when we move on cloud, that is even more important because the throughputs directly impact the cost. So the summary is the Kubernetes default scheduler was not created to tackle these challenges. So it was built for the services, long-running services, but when it comes to such complex scenario, it just doesn't work. That's when we come up with the idea that why we just create another scheduler to fix these gaps. So in early of 2019, we started a project called the YuniKorn, and right now it is Apache incubator project. And simply put, this project is a standalone resource scheduler for Kubernetes, and it is focused on building the scheduling capabilities to empower big data on Kubernetes, which one most important part is to support Spark. And it is very easy to use. It is a stateless service running on Kubernetes, and you can easily bring it up by using the Helm charts. And also it can be used as a secondary Kubernetes scheduler or the replacement as the default scheduler, because it is the full functional Then let's take a look how the resource scheduling is done in YuniKorn for Spark. Remember the workflow for the scheduling in Kubernetes is very simple, 3 steps. First one is the user submits a bunch of applications. Then the API server creates a bunch of pods for the application. And in this blue box, the resource scheduler, we'll have some scheduling logic to determine which node I should put allocate the pod. Then the step 3 is to bind that pod to the specific node. When we look at the default scheduler, it works very simple. So when the pods get created, the scheduler get notified, and all the pods will be put in a queue, in a worker queue. And when the scheduler runs a loop to select a pod from the queue, and at the same time, there's it caches all the nodes information, do a sorting, and find the best node for the pod. And then let's look at what happens in YuniKorn. So in YuniKorn, the major difference is when the pods are found in the scheduler, they will firstly be recognized as applications. And each of the application will be attached into a certain Lyft queue in the hierarchy. And when the scheduler does the scheduling, it actually first step is to traverse all the queues, find the queue where it has the most desired resource, and then instead of this queue, traverse all the applications, find the application where it desires the most resource, and then pick up the most important the request inside of the application by the priority. And at the same time, we also cache the nodes info and find the best node for the request. The rest of the step is all the same. So bind the pod to the node. So what we can get from this architecture. So basically, YuniKorn has the queue app concepts, which provides the job scheduling capability and also the fine-grained control on the resource quotas. If we compare the default schedule with YuniKorn, we can list these features where we can benefit from YuniKorn scheduler. The first one is scheduling at the application dimension. So in YuniKorn, application is the first class citizen, and YuniKorn scheduler orders the application, for example, application submission time, or the priority, or the resource usage based on the policy you choose. And secondly, the job ordering is also enforced in YuniKorn. It supports the FIFO, the fair and priority ordering policies. Then the fine-grained resource capacity management. Basically, in YuniKorn, we divided the cluster resource into hierarchy of queues, and each of queue can be configured with the min and the max resource, gives the user the guaranteed resource and the max. And the resource fairness is enforced across these queues. And more importantly, YuniKorn natively supports the big data workloads. So we have done a lot of optimizations for the big data compute engines such as Spark and Flink and TensorFlow. And so user doesn't need to modify anything from the application side, and they can easily work with YuniKorn. And also for the scale and performance, YuniKorn is optimized for performance. It has much better performance than the default scheduler. Then a little bit more detail about how Spark is running in YuniKorn. So first, so this chart gives you demonstrate how this works underneath. There's 3 layers from user's perspective, from the Kubernetes cluster perspective, and what happens in YuniKorn. And from left to right is the timeline. So first, the user will submit a Spark job, and it could be either the Spark submit or from the Spark application CRD. And what user will see is the driver pod get created on Kubernetes and with the status pending. And then underneath, YuniKorn will be notified the pod is created, and it will create an application. And the application will be added to one of the Lyft queue. And then the second stage, this YuniKorn will run the scheduling cycle, traverse the queues, find the application, Spark application, find the driver pod, then schedule the driver pod onto a node. Then what user will say is the driver pod is pending, but then once the scheduling is done, YuniKorn will, in the third stage, YuniKorn will ask the API server to bind the pod to a certain node. And then in the Kubernetes cluster, the pod is, you will say the pod is bound. We will say the user will say the Spark driver is running. Once the driver is running, the driver will start to request for executors. And on Kubernetes, the executors are created and they will be all in pending state. And in YuniKorn will get notified there are some new executors for this job. They will be added to the job. Then the next stage, we will do the same scheduling cycle as we do for the driver. Traverse the queues and the app and the request and allocate a pod on the node. Then eventually we do this repeatedly for all the executors, and all the executors will be bound. There's one more stage being skipped by this slide is after a while the job is finished. That means the executor will be finished, get cleaned up by the driver, then the driver will be complete. Then in next section, we will deep dive into some of the YuniKorn features and why they are important for Spark, and including some of the performance numbers. First is the job ordering. We've been talking about for a couple of times. So why it matters? Because from the user perspective, they usually expect there are some certain 3 use cases. So one is if I submit a job earlier, I want the job to run first, right? The second case is I don't want my job run. I don't want my job get starved because some other job or some other user use my resource. And the third use case is I have an urgent job. I want to run first. So to support all these scenarios, YuniKorn has the pluggable sorting policy, which includes the FIFO, the FAIR, and the priority. So priority currently is working in progress, and it will be released in 0.9. The next main feature is about the resource quota management. So for existing Kubernetes clusters, users are very familiar with the namespace resource quota, which defines the resource limits. And actually, it's enforced by the quota automation controller. It's not even done by the scheduler. The resource quota is not enough for the scenarios to run Spark. There are several problems with the resource quota. One is it is very hard to control when the resource quota are overcommitted, because to get a certain utilization of the cluster, the resource quota, the namespace is always overbooked. So in this case, it's very confusing and very hard for user to set up a reasonable quota for each of the namespace. And secondly, user has no guaranteed resource, which means even you have a quota, it's possible that you could not get any resource because some other namespace or some other user is using your resource. And third is the quota could be abused. By that, I mean, in a traditional batch system, there are always some pending jobs or pending pods. In that case, even for the pending pods, the quota will be used. And in that case, the utilization is really bad. And also, it doesn't provide any queuing for the jobs. All these summarized together, it will lead up into some problem like the utilization is really low, and also the latency of the job could be impacted. The alternative way to manage the quota is using the YuniKorn queue capacity. And the queue provides an optimal solution to manage the resource quotas. Why I say that? There are basically a few reasons. One is the queue can be mapped to one or more namespaces automatically, which means this gives you the zero configuration, zero overhead for the queue management. Secondly, the capacity for YuniKorn is elastic from min to max, which means the user will get the guaranteed resource for the queue and also have the max enforced. Third, the queues honors the resource fairness, which means we enforce the fairness, resource fairness between the queues, and it will help to avoid starving jobs and users. And then the quota is only counted for the pods which actually consume the resources. That means the resource counting for the job is more accurate, and also it can help to improve the utilization. And at last, the queue provides the job queuing, and the jobs can be queued in the scheduler, waiting for some conditions or waiting for the resources. So this way, we'll keep the client side logic very simple. This is a chart is about the resource fairness evaluation. We have done the experiments with simulated Kubernetes cluster on with 2,000 nodes and 4,000 nodes. And this is a very simple example. We set up 4 queues and we submit a lot of different pods to each of the queues. And from the chart, we can see the resource fairness is being enforced. And also, we have done some more some testing to get a throughput benchmark. These tests are done on the simulated environment, 2,000 nodes and 4,000 nodes on 20 physical nodes. And we scheduled 50,000 pods onto the cluster. What we observed is the red line represents for YuniKorn and the green line represents for the default scheduler. Roughly, we can get a twice better the performance comparing to the default scheduler in any scale. And one more thing, which is pretty important, YuniKorn is fully Kubernetes compatible, which means it supports all the Kubernetes predicts, node selector, pod affinity, anti-affinity, taint tolerations, and so on, and also supports the volumes, volume bindings, dynamic provisionings, and it is integrated with the Kubernetes event system, where you can get events from directly to describe the pod. And also it works with the cluster autoscaler, and this is actually one of the most important use case for us too. And it supports the management commands like Quota nodes. So on the other hand, YuniKorn provides a management console, gives its user an overview of the cluster resource utilization and also the applications running in this cluster. This is the summary cluster info page where you can get an overview about how many applications are running and some of the historical info. And there's also the nodes page where you can get the idea about how many nodes are running and the resource utilization for the nodes. For the application, similarly, we can have a list of applications showing up in this page where you can actually view the applications and their allocations. You can also try to filter the applications by search using using some of the keywords. And it also provides a view for the queues where you can view the hierarchy of the cluster, hierarchy queue of the cluster, and each of the queue, what kind of utilization it is right now. So this is very important, useful for admins to manage the cluster. And compare YuniKorn with other Kubernetes schedulers. So in SIG scheduling, except the default scheduler, there's another scheduler called a Kubatch. So we do a simple comparison here. This is majorly based on the functionality. From our perspective, we think there are main features need to cover for the scheduler are resource sharing, resource fairness, preemption, gun scheduling, bin packing, and throughput. So basically, when we compare to them, YuniKorn has all these features built in. And for the throughput, we have done some comparison with the default scheduler side by side. but we haven't done any testing with kubebatch. But based on the existing issue, I think it might not that good. Then let's talk about the community in summary and some of the roadmap. Current status of the project. So YuniKorn was open sourced at July 2019, and it enters the Apache Incubator since January 2020. And the latest stable version is 0.8, which is released on May. And right now we have a very diverse community with members from Alibaba, Cloudera, Microsoft, LinkedIn, Apple, Tencent, NVIDIA, and all these members are giving a lot of good feedback and help us to build a comprehensive scheduler to satisfy all the needs we just talked about. And from the community side, we already have some early users in the community, and the first one is Lyft. So Lee, do you want to introduce Lyft part?
Sure. So on the community, on the Lyft side, we deployed the early version of the YuniKorn scheduler in along production Kubernetes clusters in early 2020. And we launched hundreds of large jobs per day on those long production clusters with the YuniKorn queues, dedicated YuniKorn queues. And from our observation for some of the large jobs, the scheduler latency has been reduced by a factor of 3x during some peak time. And then we've also noticed on those large job clusters, the Kubernetes cluster overall resource utilization has improved in terms of cost per compute over the default kube scheduler for the mixed workload. And lastly, the requirements of FIFO and FAIR requests are more frequently met than before comparing to the default schedule. Back to Wei.
So in Cloudera, YuniKorn is shipping with the Cloudera public cloud offerings, and it provides the resource quota management and advanced job scheduling capabilities for Spark. And more importantly, it is responsible for both Microsoft service and the batch job scheduling. So it's used as a replacement as the default scheduler. And it is running on cloud with auto scaling enabled. And in Alibaba, so Alibaba is an early community user for YuniKorn and also a very important member in the community. So Alibaba deployed on the pre-production environment with over 100 nodes for a while, and that is measured on Prime. And they plan to deploy on 1,000 more nodes in production use for this year. And this is, so Alibaba is leveraging YuniKorn features such as hierarchy queues, resource fairness to run large-scale Flink jobs on Kubernetes. And from the observation that we observed there's almost 4 times improvements for the scheduling performance. And the roadmap. So currently 0.8 is the latest datable version and already shipped with a bunch of features such as hierarchy queues, cross queue fairness, fair FIFO job ordering policies, fair bin packing, node sorting policies, self-queue management, plug IP discovery, metric system, promiscuous integrations. This is a long list, but one simple summary is YuniKorn can be used as a primary scheduler to support the use case to run Spark, run big data. And the coming 0.9, we are working on the gun scheduling, job and task priority support, and also to support Spark dynamic allocation. Put all those things together, this is our vision. So for compute, we know that for big data, when we want to move big data from legacy Hadoop clusters to Kubernetes, we want to there's certain computes to be able to run lessly on Kubernetes. That includes the data engineering, real-time streaming, machine learning, and the compute engines such as Spark, Flink, Hive, TensorFlow, and so on. And also the platform will need to support Microsoft batch jobs, long-running workloads, all kinds of workloads that could be happening in the cluster. And also for targets, from the user perspective, we want to deliver the multi-tenancy environment with the SLA enabled, with the proper resource sharing and the good utilization, good cost management, budgets, and so on. So all these things, our vision is to build a unified compute platform for big data and machine learning, which is based on Kubernetes plus the features with YuniKorn as the scheduler. So YuniKorn is still a young project, so join us in the community. We have the website listed here and some of the materials you might want to check out. And we also have some community meetings to sync up and to discuss those issues. That's all for this for the slides, and thank you